Hi, it's Loic from controlsnyc. In my last vlog, I introduced myself and the project I'm going to be working on. Now I'm going to talk a bit more about my experience learning Niagara 4. I've had access to a slideshow that's part of the Niagara 4 technical certification program, which I read through and took notes from. This covered a lot of subjects, including navigating Niagara, creating points, linking components, scheduling events, adding extensions, adding a loop object for a PID controller, alarming, histories, hierarchies, backnet, modbus, and LON. This was a great comprehensive overview of Niagara 4. I also watched videos by One Site TV and Nordicity Training that followed this training program, going step by step in Niagara and showing how it's done. I thought this was really helpful, especially because I didn't have access to Niagara on the side, because these videos were short, easy to follow and understand, and gave a good feel for how Niagara looks and works. So Niagara 4 is a framework that allows separate systems and protocols to interact with each other. A protocol is a sort of language that the devices use to talk to each other. Some examples are BACnet, Modbus, and LON, which each have a different method to collect data. Niagara has three different homes: a system home, a user home, and a daemon home. A system home is used to access general files. A user home accesses your specific files, the user's files. And the daemon home is where files are run. In order to run stations, they have to be copied from the system or user home to the daemon home using the station copier. Niagara 4 has to keep track of physical components such as an AHU, as well as data points, such as temperature, so two different types of data. Proxy points can be used to represent other systems or devices that are not in the current physical network. So these points are connected together using links. All points in general are connected using links, as seen in the wiresheet view of Niagara, which is the primary programming method for Niagara 4. Each link connects one component's output to another one's input, thereby completing a network where each device is connected and can send information. For my purposes, since I'm doing the Chrysler building, but I'm not actually doing the Chrysler building, I'm going to be using all proxy points to represent my data. There are a couple of main types of hardware. Some common components are water pumps or air handling units, also called AHUs. Their output, whether it be discharge rate, discharge pressure, temperature, or CFM, respectively, are controlled by controllers. Controllers receive this information from sensors, which constantly record data about the environment. Alarms are used to alert the system in case the outputs go outside a desired range, and those are the basic parts of the system. One important tool is a loop object, which uses a PID controller to regulate a piece of equipment. So hypothetically, let's say a water pump, as an example, is filling up a vat, which is being drained, so that the vat is at 50 gallons constantly. The loop uses a set point or desired value and a controlled variable or the current value. So these values would be, the set point would be the 50 gallon mark, and the controlled value would be whatever it is currently. Therefore, we need the water to flow at different rates at different times in order to make sure that the level stays the same. So a PID controller stands for a proportion, integral, and derivative controller. So the controller uses a proportion of the magnitude of the error of the difference between the controlled value and the set point to increase or decrease the water flow. And integral creates an input proportional to the duration and magnitude of the error. So as long as an error exists, the controller will remain working, but it will work less when the error is less. The derivative uses the rate of change of the error to regulate the speed at which the controller works, but practically it's rarely used. So using these, the controller can ensure that the water in the vat remains constant at all times or close to constant. But what if something happens? What if the controller of the pump breaks from being used for too long? That's where alarms come in. Let's say a sensor in the vat picks up that it's at 60 gallons right now, which is way out of the acceptable range. It would change the status from okay to false, or any combination of Boolean outputs that you want. In either case, it's letting the system know that something's changed and that it has to react. So this message then goes to the alarm class, which routes to an alarm recipient, which broadcasts to the network that the alarm in the vat was set off because the vat has too much water. So what if you don't want the pump to break from overuse? Then you can do a Leadlag Runtime component, which can help switch between multiple pumps. In order to do this, you'll have to use a discrete totalizer extension, which can be found in the extensions palette. This will accumulate the runtime or change of state, for example, on/off, for each pump, and will let you switch out which pump is working after a certain amount of time or after one pump gives out. In another scenario with the same vat, let's say that the vat needs to have 50 gallons of water, but on weekends it only needs 30 because it needs to be cleaned. Then you can use the schedules feature in the scheduling palette in order to create a schedule for the pump. There's a yearly and weekly scheduling feature, so you can use the weekly schedule to keep the vat at 30 gallons on the weekend, and you can use the yearly schedule to put the vat to 30 gallons on holidays or days when the building is closed. However, you're never going to have just one device like a pump. You're also going to have climate control for the building, fire alarms, and a whole lot more devices that I probably haven't even learned about, but Colin might talk about in tomorrow's video. Either way, you have a bunch of different systems all connected to each other, and in order to keep track of all of that, you can use tags to label and organize different components. So you could organize them based off of boiler, pump, AHU, so different types of systems, or alarms, sensors, devices, so different types of components, or you could do both, anything that you want. So how do we program these together? First, we have to think about what kind of data each component takes as an input and an output. The most common types of data for this would be an analog and binary. An analog data point is a number, such as a temperature reading or a pressure reading. A binary point is a yes or a no, on or off, true or false. So anything with a 0 and a 1, like binary, one of two choices. So different pieces of equipment need different types of data to work. For example, you wouldn't be able to link a sensor with a temperature reading, which is an analog point, with a fan that can be only turned on or off, since the sensor has an analog output, or AO, and the fan has a binary input, or BI. Therefore, you need a function in between to tell the fan whether or not it should turn on or off based on the analog input. Therefore, I'd use a T-stat in this case, since it could compare the temperature reading with the desired temperature and then turn that into a binary input to tell the fan whether or not to turn on or off. So here's part of a system that I drew up based on a VAV, or variable air volume, which is a type of ventilation system. Firstly, you'd have sensors that record data about room temperature, the temperature of the air inside the vent going in, and the temperature of the air in the vent going out. Both of these would send their analog outputs to a controller. I'm going to use a loop object PID controller, which takes analog inputs. The controller would decide, based on this data, whether or not the room has to be cooled or heated, and would then send an analog output to a damper to close or open the duct by a certain amount. Now, the temperature sensors would also need some alarms to connect to them in case they detect a temperature that's outside of the desired range. So an alarm would first route to an alarm class and then an alarm recipient. You could have multiple alarms to detect off-normal temperatures, so something not too far off from the desired, as well as critical failures, so temperatures way off that could be unsafe. I'm not going to worry about that right now. I'm going to first focus on simple systems with just having one type of alarm, and then I'll add that in at the end. Keep in mind, this is not a full VAV system, since you'd have a similar system in place for the same network for air pressure, quality, and humidity, so a lot more going on. So that's all that I've learned from my first days here. A great resource in this was OneSite TV's videos. They follow along the technical certification training program, and they help all this make a lot more sense to me by giving visual examples of what I'm talking about. Nordicity Training also has some great videos. They're very easy to follow, but they don't go quite as in-depth as some of the other ones. If you have any questions, please leave a comment down below. Consider subscribing. Thank you so much for watching. I'll see you soon.